So to take it from here, determinants. This is another example and a review of the 2 or 3 that we've done already. If you will just go through these, take these one step at a time, open this up, take a look at it, write out each step, make sure that you understand the process here. This lays out the characteristic determinant, and how we solve for that. You can see that in this slide. Substituting then resistor values for voltage values, then, as we've seen before, solve for the individual current. So we replace the values in the first column in each case so that we can solve for the individual currents, and that's what we've done here. And so we get our determinants there. And then we can go through by dividing through by the characteristic determinant into the individual determinants for the current. So for current 1 and for current 2, you can see the relationship. So this one is just a good working example for you to go back through and make sure that you do in fact understand the process. Okay, so you can see then in solving for these, again, this is just a rehash of what you've already seen. Use it as a learning tool. Same thing here. In this case, we are rehashing the three coefficient, third order, and you can see again step by step how we solve these. Okay, determinant for current 2, again, just as we solved in the previous video. So now we move into something called the branch current method. The branch current method is a circuit analysis method using Kirchhoff's voltage and current laws to find the current in each branch of a circuit by generating simultaneous equations. Once you know the branch currents, you can determine the voltages. So you can see in these in the example below, the circuit showing the loops, the nodes, and the branches in a simple circuit. Okay, so a loop is a complete current path within a circuit, and you can view a set of non-redundant closed loops as a set of, quote, window panes, where each window pane represents one non-redundant loop. Also, there are 4 nodes as indicated by the letters A, B, C, and D. So we've seen now in many examples here that the nodes are the way that the current moves in and out of. All the current into the node, add up, all the current out of a node, subtract. So a node is a point where 2 or more components are connected. A branch, finally, is a path that connects 2 nodes, and there are 3 branches in this circuit. One containing R1, one containing R2, and one containing R3, as well as the 2 voltage sources. So in the branch current method, the general steps are as follows. Assign a current in each circuit branch in an arbitrary direction. So they're telling you it doesn't matter if you think this is the way the current flows, choose that and stay with it. The signs will bear out if you chose it right or wrong. Show the polarities of the resistor voltages according to the assigned branch current direction. So positive to positive, negative, negative, positive to positive, and then positive and negative according to the batteries. Okay, so then we apply Kirchhoff's voltage law around each closed loop, which was the algebraic sum of voltages that equal 0. Finally, then we're going to apply Kirchhoff's current law at a minimum number of nodes so that all the branch currents are included. The algebraic sum of currents at a node, again, must equal 0. Then solve the equations resulting from steps 3 and 4 above for the branch current values. So these steps are demonstrated with the aid of this figure. First, the branch currents I1, I2, and I3 are assigned the direction shown, just as the step says. Don't worry about the actual current directions at this point. Second, the polarities of the voltage drops across R1, R2, and R3 are indicated in the figure according to the assigned current directions. Third, Kirchhoff's voltage law applied to the two loops gives the following equations where the resistance values are the coefficients of the unknown current. So you can see we're putting these in kind of a standard form here. We've got our voltages on the left side here. So we've got R1, I1, R2, I2, and the same thing for equation number 2. So loop 1 and loop 2 current equations or loops relationships are spelled out here. Fourth, Kirchhoff's voltage or current law is applied to a node. Okay, and we're going to choose node A here in red, including all currents as follows. So we have current 1 going into the node, current 2 leaving the node, current 3 going into the node, and the sum of those have to be 0. The negative sign indicates that I2 is out of the node. Fifth and last, the three equations must be solved for the three unknown currents, I1, 2, and 3. The example circuit shows how to solve equations by using the substitution method. Okay, so make sure you understand that process, and what we'll do when we come back is we will solve this type of problem. It will look just exactly like the example for branch current method.